Welcome to BD Deep Dive, where ideas go deeper. Today, we're stepping into what is basically the most expensive group chat on Earth, GPUs trying to talk to each other fast enough to train modern AI. This deck frames it as a connectivity war, because whoever controls the links between accelerators controls performance, cost, and ultimately, who can afford to compete.
And it's not just a nerdy cable debate. Interconnect decisions shape everything: how big a cluster can get, how reliably it trains, and whether you're paying for premium performance or betting on open standards. So if you've ever wondered why the network suddenly sounds like the star of the AI show, this is why.
The key setup is simple. Model sizes went exponential and the bottleneck moved. It used to be, how fast can a GPU compute? Now it's, how fast can a whole pile of GPUs synchronize? When training time is dominated by communication time, moving gradients, weights, activations, your fancy compute turns into very expensive waiting.
So the mental model is, the GPUs are chefs, but the kitchen is chaos. If ingredients can't get from station to station quickly, the chefs just stand there. And AI training has tons of small, frequent ingredient transfers, those synchronization steps, so latency and consistency start to matter as much as raw throughput.
The deck splits the war into three fronts. First, the data center fabric, rack-to-rack networking at scale. Second, the scale-up fabric, inside a server, GPU to GPU. Third, the emerging frontier, new architectures and standards that reshape what a GPU system even is, including consumer and physical layer shifts.
I like that framing, because it stops us from arguing like there's one universal winner. The best choice depends on where you're connecting things, across racks, within a chassis, or across an entirely new kind of modular system. Different physics, different costs, different failure modes.
On the data center fabric front, the deck reminds us that InfiniBand dominated AI training clusters in 2023, estimated around 80% share. The reason is its predictable ultra-low latency, especially for small messages. That's perfect for those frequent training updates, where jitter can be as painful as slowness.
Right. Small message latency is the unsung hero. People hear bandwidth and think it's like pouring water through a pipe. But training often looks like lots of tiny packets that must arrive on time, repeatedly. If you're coordinating thousands of GPUs, a few microseconds here and there can cascade into real idle time.
Then comes the plot twist. By 2025, Ethernet is leading AI backend network deployments. Not because it magically became perfect, but because tuned RoCE latency lands around 1.5 to 2.5 microseconds, close enough to InfiniBand's roughly 1 microsecond for many training workloads, especially when engineered carefully.
And the deck calls out the ecosystem push, the Ultra Ethernet Consortium, plus AI-optimized silicon from major vendors. The big credibility stamp is Meta, validating equivalent performance to InfiniBand on a massive Llama 3 cluster using RoCE. That's not a lab demo, that's a production-scale proof point.
Now, the deck basically says, for most buyers, economics decide. For a typical 512 GPU cluster, Ethernet saves over $1.18 million in hardware upfront. And when you include operational costs, the 3-year total cost of ownership gap grows to $2.24 million. That's not nice. That's strategic leverage.
The deck's comparison is deliciously blunt. That savings can fund an additional 64 H100 GPUs, or extend a startup's runway. So even if InfiniBand is still the latency king, Ethernet becomes the more GPUs now option. And in AI, buying more accelerators often beats shaving the last microsecond, especially for Tier 2 and Tier 3 orgs.
Switching to the scale-up fabric, inside the server, NVIDIA's NVLink is positioned as the gold standard. The key idea is a direct mesh that lets GPUs communicate without CPU intervention, minimizing latency. And the bandwidth figure here is eye-watering. The 5th generation delivers about 1.8 terabytes per second bidirectional per GPU.
That no CPU in the middle part matters. It's like replacing a busy receptionist with a private hallway between every office. Less contention, fewer detours, less overhead. It also explains why people talk about proprietary stacks. The interconnect isn't just a cable, it's a tightly integrated system design choice.
But the standards world is fighting back. The deck points to a problem in legacy PCIe controllers. At very high speeds, serialization creates bubble cycles, wasted bandwidth where the link sits idle because traffic patterns are bursty and hard to pack efficiently. That's deadly for complex AI communication patterns.
And the proposed fix is basically stop treating the link like a single-lane road. PCIe 6.0 and 7.0 introduce multi-stream architecture, processing multiple data streams in parallel. If it eliminates those idle cycles and boosts utilization by 80% for AI-like traffic, that's a big deal because theoretical bandwidth finally looks like usable bandwidth.
Even with PCIe 7.0 improvements, the deck highlights a stark gap. NVLink 5.0 around 1800 gigabytes per second versus PCIe 7.0 x16 at roughly 28% of that. So an alliance forms, the Ultra Accelerator Link, UALink, aiming to build an open, high-performance scale-up standard rather than leaving the whole inside-the-box story to one vendor.
The clever bit is that UALink leverages the proven PCIe 7.0 physical layer, but adds a more efficient protocol stack tuned for AI workloads. So it's not reinventing the wires, it's optimizing the rules of the conversation. That's often where performance hides: flow control, ordering, congestion handling, and not doing extra work per message.
Now to the emerging frontier, deconstructing the GPU itself. The deck argues the industry is pivoting from massive monolithic dies towards clusters of smaller Lite-GPUs. The why is manufacturing reality. Smaller chips tend to yield better. The claim here is about a 1.8 times yield improvement and nearly 50.
And it reduces the blast radius of failure, conceptually. If one giant die has a defect, you lose the whole expensive slab. With smaller modules, you can bin, mix, match, and recover value. But to make that modular cluster behave like one coherent accelerator, you need insane connectivity. Enter co-packaged optics, integrating optical engines onto the substrate to break copper bandwidth limits.
And the war doesn't stay in the data center. The deck compares a Mac Studio cluster to an NVIDIA DGX Spark-style system. The consumer-side story is unified memory and inference efficiency, with Thunderbolt 5 at 80 gigabits per second and, crucially, RDMA plus memory pooling as the enabling tricks for local, efficient inference on massive models, up to multi-terabyte pooled RAM in the framing here.
Well, the DGX-style approach is the classic raw training power story. Higher bandwidth networking, like 200 gigabits per second class interconnect, plus NVLink and the CUDA ecosystem. So it's almost two philosophies. One is make inference practical and local with clever memory and RDMA. The other is build the purpose-built supercomputer and live inside the proprietary performance universe.
Then the deck drops the software multiplier. You can make existing hardware feel bigger. Power Infer is highlighted for exploiting activation sparsity, keeping hot neurons in fast GPU VRAM while cold neurons live on the CPU. So consumer GPUs can run models that would otherwise look impossible on paper.
And XO is the orchestration angle, an open-source platform for peer-to-peer clustering across heterogeneous devices, Macs, even phones, using auto-parallelism and RDMA to act like one distributed inference engine. It's the Voltron approach. Each device is modest, but coordination turns the pile into something surprisingly capable.
The deck wraps the forward view into three trends. 1. The push for openness. Alliances like UEC and UALink challenging proprietary ecosystems with interoperability and lower costs. 2. The physical barrier. Copper hitting limits, making optical interconnects like optical PCIe and CPO basically mandatory beyond certain scales. 3. Software primacy. Sparsity and orchestration multiplying efficiency.
That's a nice trifecta because it links strategy to physics. Openness is politics and economics. Optics is the unavoidable reality check from material science. And software is the cheat code that keeps working while everyone waits for the next packaging breakthrough. If you're planning infrastructure, you can't ignore any of the three.
Strategic conclusion. The trade-off persists. NVIDIA's vertically integrated proprietary stack versus a flexible, economical, open standards ecosystem that keeps getting more capable. And there's no single winner, because this is multi-layered. Rack-scale networking, inbox scale-up, and the physical frontier each have different best answers.
So the practical takeaway is almost boring, in a good way. Match the interconnect choice to the layer and workload, balancing cost, performance, and openness, and keep your eye on packaging and photonics, because the next generation of infrastructure leaders may be decided less by who has the biggest GPU and more by who can move bits with the least pain.